formulas of geometry turn out to be important in calculus. These are basic formulas, and I'm going to enumerate them here so that they're clear in your mind. The unit of area is that of a square whose sides are 1 by 1. Then, given that, then, the area of any square is the product of the two sides, or the sides squared. For a rectangle, with base B and height h, the area of the rectangle is the base times the height. The area of a triangle with base B and altitude h, the area of the triangle is 1/2 the base times the height. This fact here can be visualized real easily. If the triangle were a right triangle, that's to say, if the altitude lay exactly at one of the sides, then you can draw a congruent triangle over here like so, and it's clear that the area is 1/2 the area of the rectangle. If it's not a right triangle and the altitude lies interior to the triangle, like so, then it's clear that it's made up of two right triangles, and the area of this one is 1/2 the base, its base times its height. The area of this one is 1/2 its base times its height, and so consequently the area of the entire triangle is 1/2 of the sum of the two bases plus the height. That's to say, the area of the base times the height, the quantity of the base times the height times 1/2. The only other possibility is that the altitude lies outside of the triangle, like so. And in that case, the area of this triangle, right, is the area of the large triangle, the large right triangle, minus the area of the smaller right triangle, and this is 1/2 the altitude times the base. This is 1/2 its altitude times its base, so this is going to be 1/2 the altitude times the base by very simple algebra. Right. The area of a circle of radius r, the area of the circle is pi r squared. The number pi is defined to be the ratio of the circumference of the circle to its diameter, so that the circumference of a circle is equal to pi times the diameter, which is 2 pi times the radius. That's an important formula to know. These are basic areas. One other one might be included here, and that is the area of a trapezoid. A trapezoid is a figure that has two parallel sides, and if it has a lower base B1 and an upper base B2 and an altitude h, then the area of a trapezoid is the average of the upper base and the lower base times the height. All right. Several formulas involving volumes are also going to occur at various points in time, and they're worth knowing. Some of them will be derived eventually within the calculus. The volume of the sphere is 4/3 pi r cubed. And the surface area of the sphere is 4 pi r squared. For rectangular parallelepiped, box shape if you like. The volume is equal to the height times the width times the depth. So this is the height, the width, and the depth. One further formula which is quite useful, and that is the volume of a cone or of a pyramid is equal to 1/3 the area of the base times the height. This will eventually be derived in calculus, as will the volume and surface area of the sphere. A cone, one example is a right circular cone, looks something like this. Here's the height. The area of the base is pi r squared, the area of a circle. A pyramid may look something like this. It's a pyramid with a square base. Then the volume is going to be 1/3. The area of the base is going to be the side squared times the height, which is the perpendicular height. This holds true in general, though, for even unusual cones. If a cone is defined by taking an area here, A, and a point not in the plane of the area, and drawing all of the line segments connecting this point to the area, you end up with a cone that looks something like this. Right? It's still true that the area of the cone is the height times the area of the base. And this altitude need not lie over the cone. So that, for example, if the cone looked like this, and this was the altitude, the resulting volume of a general cone, it would be 1/3 the area of the base times the height. Those are general formulas that are going to be needed in calculus. For distances in the plane, we're going to need the Pythagorean theorem. And I'm going to show several versions of this theorem right now. The Pythagorean theorem says that in a right triangle, a squared plus b squared is equal to c squared, where a and b are the lengths of the sides of the triangle and c is the length of the hypotenuse. If we draw a triangle like so, a right triangle, with the right angle up here, right angle right there, and label the sides A, B, and C, and these two sides D and E, then what we have is that there are actually three triangles here that are similar to each other. This triangle right here, this triangle right here, and this triangle right here. Now, one of the properties of similar triangles that we're going to need in calculus is that the corresponding sides of similar triangles are proportional. That's to say, if we take the long side in the triangle here, in the big triangle, A, its ratio to C, the hypotenuse of the large right triangle, is the same as the ratio of the long side of this triangle, D, to its hypotenuse, A. Similarly, B, the short side of the large triangle, is to C as E, the short side of this triangle, is to B. If we multiply both sides of this by A and by C, we get that A squared must be equal to C times D. If we multiply both sides of this by B and by C, we get that B squared must be equal to c times e. Adding these two equalities here, we get that a squared plus b squared must be equal to c times d plus c times e, but b plus e is c, and so that this is equal to c squared. And that gives you a proof of the Pythagorean theorem. Right. This proof is clearly not the proof that was known to Pythagoras or to any of the people that worked with this before algebra was discovered or invented. I want to show you a couple of other ways of seeing that the Pythagorean theorem holds. The first uses a little algebra. If you draw a triangle like so, a right triangle, and now construct up here a congruent triangle to the first one, and similarly over here, a congruent triangle to the first one, and finally complete the square here and construct a fourth congruent triangle to the first one. If this is A, and this is B, and this is C, then the area of this whole thing is equal to c squared plus 4 times the area of a triangle, where this is the triangle T here. But the area of the triangle is equal to 1/2 the base times the height. So 1/2 A times B, or B times A. So this is equal to 4 times this. And another way of computing the area of the entire thing here is this is B, and this is A, and so the area of the entire thing here is also equals to A plus B quantity squared, which is equals to A squared plus 2AB plus B squared. This supposedly must be equal to 4 times 1/2 BA plus C squared. That's to say this is equal to C squared plus 2AB. Or, subtracting this from both sides, we get that A squared plus B squared is equal to C squared. This clearly uses some algebra, but not quite as much geometry as that one does. Perhaps the way in which this was originally known is as follows. If a triangle is put here like so, one can then put a square on the hypotenuse, like so, construct this congruent triangle, and this one. Oh, I guess I will not need the bottom one here. Leave this out of the picture. That's this one. And this one. And complete this like so. Then the resulting area of this rather bizarre shaped figure is the area of the square on the hypotenuse plus 2 triangles. This triangle here and this triangle here. But it's clearly also equal to the area of the square of a side. This is the square right here with this for its side length, plus a second square with the other side for its side length plus 2 triangles. So this is equal to A squared plus B squared plus another two triangles, which shows in a third way that a squared plus b squared must equal c squared. This picture apparently had been found on several stones of ancient origin, and it's the reason for believing, perhaps, that this was well known, that the Pythagorean theorem held even to even earlier civilizations. So there they are. We now want to consider the coordinates plane. This is obtained by taking two real lines and drawing them perpendicular to each other, putting the units on here. This would be 1 unit, and so forth. And similarly in this direction here, likewise like so. And down here. And then any point that occurs in the plane will correspond to two real numbers. The coordinate on the x-axis is being called the x-axis, or abscissa, and the second coordinate on the y-axis. And similarly, any pair of real numbers will correspond to a point in the plane. So the points in the plane are represented with open parentheses as a pair of real numbers. This is no doubt known by most people who are taking calculus. This is a review at this point. All right. Points like so. Given the coordinate plane, this area right up here on the upper right is called the first quadrant, the second quadrant, the third quadrant, and the fourth quadrant. So that, for example, here, this might be the point 2.5, 3.1. Anything that's in the first quadrant has both of its numbers in the pair positive. Here might be, for example, the point minus 3, 2. Its x-coordinate is minus 3. Its y-coordinate is 2. Here would be perhaps the point minus 3, minus 4. And here perhaps the point 2 minus 4. Every point in the plane corresponds to a pair of real numbers, and every pair of real numbers allows you to locate a point in the plane. If we're given two such points, say this one, let me call it x1, y1, and the second one, x2, y2. Then joining those two is a line segment. And we want to know two things about this line segment. One, we want to know where the midpoint of the line segment is, and secondly, what the length of the line segment is. The length of the line segment will define the distance between the 2 points. So first of all, the midpoint of a line segment from x1, y1 to x2, y2. Well, while I'm drawing this over in the first quadrant, this picture is perfectly general, no matter where the points x1, y1, and x2, y2 are located. we wish to do is to construct a triangle here with this line as its hypotenuse. Now, if there is a possibility, of course, that this line be either horizontal or vertical. I'll talk about that in a moment. However, assuming that we get a triangle as a result of doing this, we find that the midpoint, if we bisect this line, the midpoint determines two congruent triangles here. And that, since these two triangles are congruent, this length here is equal to this length is equal to this length. And so that the x-coordinate of the midpoint should be the point whose distance to these 2 points, the two x-coordinates, is equal. And that's going to be exactly the point that's the average of the two x-coordinates. Its distance to x1 is exactly equal to its distance to x2. Incidentally, the distance between 2 points, x1 and x2 on the line, is given by the absolute value of x2 minus x1. This holds in general if the points x2 and x1 are in either configuration. If x2 is to the right of x1, then it's going to be x2 minus x1. If x2 is to the left of x1, then it's going to be x1 minus x2. And that's to say it's going to be the absolute value of x2 minus x1. So the distance between 2 points on the line is given by absolute x2 minus x1. Now it's real easy to check then that the distance from x2 to x1 plus x2 over 2 and the distance from this to x1 are exactly equal, so that the x-coordinate of this point is going to be x1 plus x2 divided by 2, the average value of the two x-coordinates. And a similar consideration over here shows that if this is y1 and this point up here is y2, then this point right here is y1 plus y2 divided by 2. So the y-coordinate of the midpoint of a line segment from joining 2 points here is going to be y1 plus y2 divided by 2. Now what about the distance between these 2 points? Well, by the Pythagorean theorem, this distance here, we write it as d, this distance squared is going to be equal to this distance squared plus this distance squared. That's to say the distance squared is going to be x2 minus x1 in absolute value squared plus y2 minus y1 in absolute value squared. Now, since it doesn't make any difference when you square a number, whether it's positive or negative, squaring the absolute value is the same as squaring the number itself. These absolute value signs here are frequently not put there, but rather parentheses are. The distance between 2 points, x1, y1, and x2, y2, is then given by the fact that the distance squared is equal to x2 minus x1 squared plus y2 minus y1 squared, or the distance itself is equal to the square root x2 minus x1 squared plus y2 minus y1 squared, where here the square root, as usual, means the positive square root. So here then we have the midpoint of a line segment and the distance between 2 points. coordinate plane, into 2 points, x1, y1. Again, I'm drawing these in the first quadrant. There's nothing special about doing so. These 2 points determine a unique line. We want to know the equation of that line. Perhaps best to begin, rather than with 2 points, but with a single point, x naught, y naught, and what's called a slope. If we proceed over to the right here, 1 unit, the amount of length, the perpendicular here, determines what's called a slope. If this is in the positive direction, then this number m is positive, and the line is said to have a positive slope. If the line is horizontal, it's said to have slope 0. If the line is heading downward, then proceed 1 direction over here, and the negative number here will represent the slope, the number m less than 0, where you proceed 1 unit over in this direction and 1 down here. Now, given a point and a slope, a unique line is determined by the point and the slope. And the way to determine the equation of this is to consider a general point xy on the line. What does xy have to do to get on the line? Well, this triangle right here, determined by xy, must be similar to the triangle right here. That's to say that this distance, y minus y naught, to this distance, x minus x naught, must be proportionate to m to 1. That's to say, must also compute the slope. Right? Or the equation of the line multiplying this across here is given by y minus y naught is equals to m times x minus x naught. One should note that that's really easy to derive if you're given the point x naught, y naught, and a slope m. It's really easy to derive this. Now it's also easy to check that this will hold if m is equal to 0, in which case we get y is equal to y naught is the equation of the line. And then if m is negative, then this equation here holds for all points x, y on the line except for the point x naught, y naught. And that's the reason for calling this the equation of the line. This equation doesn't make any sense at the point x naught, y naught, because we end up with 0 over 0. So the equation of the line, given a point and a slope. I want to mention that it is not really worthwhile memorizing this or the other equations that we get because they're so easily derived. Let's suppose now that we've got 2 points, x1, y1, and x2, y2. Well, then we can compute the slope of this triangle here. The slope is going to be y2 minus y1 over x2 minus x1. And this will hold true even if the line happens to be horizontal. Vertical lines don't have a slope, and so this really is the equation of non-vertical lines, or of a non-vertical line. All right, so if we're given 2 points, then this is the slope, assuming the line is not vertical. And you can check this also if the slope happens to be negative, that this will be a negative number, and will correspond by similar triangles to the actual slope m. Now, a third point, xy, gets on the line here. When we compute the slope using xy, we get the same quantity. That's to say, if y minus y1 over x minus x1 is equal to this. Now again, this equation holds except at the point x1, y1. And so the actual equation that we want out of this is going to be achieved by multiplying both sides here by x minus x1 and by x2 minus x1, and getting y minus y1 times x2 minus x1 is equal to x minus x1 times y2 minus y1. Again, this is not an equation that's worth memorizing. It is, however, worth noting that all of these numbers here that I'm underlining right now are fixed quantities, and so that similarly here, the equation of the line only involves y and x and numbers. In the event that you know where the line crosses the y-axis, the number b is called the y-intercept. If the line crosses the axis here at the point 0b. If the slope of the line is then m, then the equation of the line is y equals mx plus b. This can be easily gotten by writing here that y minus b divided by x minus 0, or just x, must be the slope. This is the equation of the line in the event that it crosses the y-axis at the point 0b and has slope m. This is a frequently memorized equation for a line. It's kind of neat. Right? There's another equation that's somewhat neat, that's memorable for a line. That's to say, every line is of the form ax plus by plus c is equal to 0. Every line. Right? That's because the lines that we have avoided here, the vertical lines, ones that go through a point here and are parallel to the y-axis. This line right here, if it goes through the point A0, is going to have all of its x-coordinates equal to A. And so its equation is x equals A. So one equation of a line is x equals A. If the line happens to be vertical, y equals mx plus b if the line is not vertical. Now, to see that this takes care of all possible cases, there are really two possibilities here. One is that the number b is equal to 0. Oh, I should mention that both a and b are not supposed to be 0 in this equation. So one possibility is that b is equal to 0, in which case we can subtract c from both sides here and get x is equal to, well, ax is equal to c, or minus c, or x is equal to minus c over a. That's this case right here where x is a fixed number. So if b is equal to 0 in this equation, then you're dealing with a vertical line. If b is not equal to 0, then this equation here can be solved for y by subtracting ax from both sides and subtracting c from both sides, that we have minus ax minus c is equal to b times y. And now dividing by b, we get that y is equal to minus a over b minus c over b. And then this is of the form y equals mx plus b. The m is minus a over b. The b, little b, is minus c over b. So it's clear that these are the two possible types of lines, and that this equation right here is the general equation for a line. For the other cases, it's a good idea to be able to do this type of thing, but I certainly wouldn't memorize a formula that looks like this or this in order to be able to do it. We're going to consider the intersection of two lines. Two lines need not intersect. If they're parallel, they won't in particular. And in fact, that's the definition of parallel. Huh? If they're parallel, they're not going to intersect. You've got two parallel lines which aren't vertical, and they have the same slope. In either of the two convenient forms for writing a line, this is apparent. If we have, for example, y equals 3x plus 4 and y equals 3x plus 5, the slope is right here, and it's clear that those have the same slope, and so consequently they're going to be parallel. In the other convenient form, this is in the form y equals mx plus b. The other convenient form, ax plus by plus c equals 0. If we have something like 2x plus 3y plus plus 4 is equal to 0, and 4x plus 6y plus 7 is equal to 0. You could easily solve this, for example, and put it in this form, or frequently you could recognize the proportionality of 3 to 2 and 6 to 4, and so that consequently, in this case here, you could recognize from the shape of this equation, these two equations, that these are two lines which are parallel. These are parallel, and those are parallel. Right? If you do not have the equal slope in this form, or if you do not have proportionality here like so, well, that's to say if you were to put it in this form, you'd have equal slope, then the two lines are going to meet. And two lines in the plane, which are not parallel, are going to meet in a point. We want to find out how to find the x and y coordinates of that point. Let's take a look at an example of lines either given in this form or in this form. The way to find the x and y coordinate basically is to solve the two equations together and find out which number xy satisfies both of these two equations. So that, for example, if we had y equals to a half x minus 3 and y equals to a fifth x plus 7, say. Those are two lines. They do not have the same slope, and so consequently they're going to meet in a point. The way in which we can find that point, if we're given them in this fashion right here, is to find the x coordinate by equating these two quantities. That's to say, 1/2 x minus 3 equal to 1/5 x plus 7. Right. Then what must happen here? Adding 3 to both sides, we're going to get 10 here. Subtracting a fifth x, we're going to get a half minus a fifth. X, a half is 5/10 and a fifth is 2/10, so this is going to be 3/10 x. So that x will be equal to, when we multiply both sides by 10/3, 100 over 3. Right? Now if we put this number x back into either of these two equations, we're going to find one number y, in particular here, that y is going to be equals to 1/5 times 100 over 3 plus 7, right? And then the pair of numbers, 100/3, what is this, 20/3 plus 21/3, this is 41/3. Let's check. 20/3 and 21/3 is 41/3. That's the pair of numbers, 100/3, 41/3 is going to be the point where these two lines intersect. Let's look at the other form. Suppose we have two lines like this. 3x plus 4y equals 5. 6x plus 7y is equal to 8. Oh, let's make this minus 7y. All right. If you're given this in this form, clearly you can change it over so that it's in this form here and go through this procedure here. However, one can solve these two equations together to find a point xy that satisfies both of them by a simple procedure of multiplying the first equation and the second equation by a constant and subtracting this two, so that the x term here, for example, would drop out of the picture. For example, if we multiply the first equation here by 6 and the second one by 3, the resulting equations will both have 18x. All right? And when we subtract the two, we will get no x term. We will be able to solve for the y term and find out what the point xy is. So if we multiply the first one by 6, we get 18x plus 24y equals 30. The second one by 3, we have 18x minus 21y is equal to 24. Right? Subtracting these one from the other, we're going to get 24 minus 21 is going to be 45. Y is equal to 6, so that y is equal to 6 over 45. That's the y coordinate of the point where they intersect. And to find the x coordinates, we need to put 6 over 45 in here for y. And we get that 3x plus 4 times 6 over 45 is equal to 5. Or that x, this is 24 over 45. 5 is well, we have 5 minus 24 over 45 divided by 3 is going to be the x coordinate, and then clearly you can simplify that. So in either case here, if we're given the point, the slope-intercept form, right, or in the form ax plus dy plus c equals 0, you may solve this too and find the point of intersection of the two lines. All right, we want to consider a situation where two lines are perpendicular. First of all, let's consider a line which has a positive slope. The equation might be y equals mx plus b. We can then consider a parallel line to this one that goes through the origin. It has equation y equals mx. And if we go over one unit here like so, the quantity m is the rise over here of the third side of this triangle. Now if we wanted to construct a perpendicular line, if we draw a triangle down here that is 1 unit by m, we will achieve this effect because what? This angle is equal to this angle, and so this angle right here must be 90 degrees. This angle right here must be a 90-degree angle. It's this 90-degree angle turned. All right? Now, so that the slope of a perpendicular line is going to be the slope of a line like so. And what is that? Well, if we complete the picture of this rectangle here, we find that 1 to m is the numerical value of this ratio. And since m here was positive, then 1 to m is going to be the slope but it's going to be minus 1 over m. It's going to be the slope of the perpendicular line. Now this is for the case where m is greater than 0 and the line is upward. If m is equal to 0, then the perpendicular line does not have a slope. If m is less than 0, though, the same quantity, minus 1 over m, is going to be the slope of the perpendicular line. And so one usually remembers something that goes like this. The slope of a perpendicular line is the negative reciprocal of the slope of the line. The negative reciprocal is the slope of the perpendicular line. Let's check that that's the case in the event that the line slopes downward. Let's draw the line through the origin with a given slope. Slope m, where m is less than 0, so this quantity here is minus m, and this one is 1. And now the perpendicular line again can be gotten by drawing a similar triangle up here, a congruent triangle, where this is 1, and this quantity is m, and then what? This will be m, and this will be 1, so 1 to m will be the slope, but it will be the negative of this quantity minus m, so minus 1 over m is the slope then of this line. So whether the line points upward or downward here as you proceed to the right, whether it's got positive slope or negative slope, minus 1 over m is the slope of the perpendicular line. Now, given a point and a line, or a point and a slope, frequently one wants to find the equation of the line that has the slope perpendicular to the given one. Now this is nothing but an old problem here. So that, for example, if we had the line 2x plus 3y is equal to 4, then we can find the slope of this line by putting it in slope-intercept form, for example. We get that y is equal to 4 minus 2x divided by 2 and divided by 2 here, right? So y is equal to minus 2x divided by 3. Y is equal to minus 2/3 x plus 4/3. The slope of the line is minus 2/3. The slope of a perpendicular line will be 3/2. Like that as m prime here as the slope of a perpendicular line. And now if we wanted a slope of if we wanted an equation of a line perpendicular to this one through, let's say, the point 5, 6, and perpendicular to this one, right? We would first find the slope of this line, minus 2/3. Note that 3/2 is going to be the slope of the line that we want. And now the equation of the line is going to be given by y minus 6 over x minus 5 is equal to 3/2. That's to say a point xy gets on this line if when we compute the slope y minus 6 over x minus 5 using the point xy, we get 3/2, or multiplying through here, y is equal to 6 minus, plus 3/2 times x minus 5. Or putting this in the slope-intercept form, y is equal to 3/2 x. What do we have here? 6 minus 15/2. That's 12/2 minus 15/2 is minus 3/2. The slope of this line here is 3/2, as it should be. It is perpendicular to this given line, and it goes through the point 5, 6. We could check that by putting 5 here for x and make sure that we get 6 for y. We now want to consider circles and equations of circles in the plane. Let's draw a coordinate system here. And let's first consider a circle centered at the origin. A circle is a collection of all points whose distance from a given point is a fixed quantity called the radius. So this is going to be the radius r here. What we want is an equation that tells you when points x, y belong to this circle. And we can do that very quickly by simply noting that the origin, which is the point 0, 0, must satisfy that the distance from this point x, y to the origin is going to be r if the point's going to be on the circle. That's to say that r is going to be equal to the square root of x minus 0 squared plus y minus 0 squared using the distance formula, or that r is equal to square root x squared plus y squared, or that x squared plus y squared is equal to r squared. So this is the circle centered at the origin. With radius r. If we wanted a circle that was centered at a different point, let's say here at the point x naught, y naught, a circle of radius r centered at this point right here, or this, let's say, is r again. What does the point x, y need to do to get on that circle? Well, it must be that this distance from this point to x naught, y naught is r. That's to say that r is equal to the square root of x minus x naught squared plus y minus y naught squared, or that x minus x naught squared plus y minus y naught squared is equal to r squared. To square this term here and square this term and combine all the constants, keep in mind that these are all fixed quantities here, you find that the resulting equation looks like this. Ax squared plus ay squared, here a is equal to 1, plus bx plus cy plus d is equal to 0. An equation of a circle is going to look like this. Clearly I could divide here by a, where a is not equal to 0, and I would get an equation that would potentially be an equation of a circle. Equation of a circle always looks like this. We're going to see momentarily how to determine whether an equation that looks like this is a circle. Right, we now wish to examine equations that look like ax squared plus by squared plus cx plus dy plus e equals 0. Such equations will have for their graph, that's to say the point xy that satisfy the equation, they will have either a circle or a point or nothing. It's perhaps easiest to see this by looking at a particular example. Suppose we consider 2x squared plus 2y squared plus 3x plus 4y plus 5 equals 0. I'm going to change this equation if it doesn't turn out to be what I want it to. Right? The first thing I want to do is I want to divide by the quantity a, so that I get x squared plus y squared plus 3 halves x plus 2y plus 5 halves is equal to 0. And then what I want to do is I want to group the x terms together and the y terms together and the constant on the other side. And I'm going to essentially complete the square of the x terms and the y terms and make this equation correct. And we'll see that we have either a circle or a point or nothing. What have we got here? X squared plus 3 halves x plus y squared plus 2y is equals to minus 5 halves. Now, how to complete the square? If you've got x squared plus ax, and we wish to add something onto this to make it a perfect square, the things to add on to it is a squared over 4. That's to say, divide the quantity a into 2 and square it. Then that this is going to be then equals to x plus a over 2 quantity squared. So that's how to complete the square here of something of the form x squared plus ax. So we want to take 3/4 here and square it and add that on here. And that's going to be, we're going to add on 9/16. And here we're going to want to take 2/4, a half, and square it and add that on. That means we're going to want to add on a 1/4. Now, of course, that's not fair to do. We can't add on 9/16 here and a 1/4 here without adding them to the other side. So we want to add 9/16 and a 1/4. We're now going to find that this is a perfect square. It's x plus 3/4 quantity squared. And y plus a half squared is this. And what have we got over here? So many 16ths here, huh? Well, we have 9/16 plus 4/16 for the 1/4 minus 40/16, or 27/6 minus 27/16. This indicates that this particular equation doesn't have any solutions, because in order for it to have a solution, you have to find points x and y so that this quantity squared and this quantity squared was a negative number. And the square of quantity is always positive, and so that the sum of two squares of numbers is always going to be positive. It's not possible to add up to minus 27. And so this does not have any solutions. If we ended up with 0 over here, instead of minus 27/16 when we solve this equation, then there would be a solution. So here we have no solutions. Here we're going to have 1. Namely, if we had the same equation here with 0 here, then when x was equal to minus 3/4 and y was equal to minus 1/2, that single point alone would satisfy this is equal to 0 and this is equal to 0, and so the sum of the two squares is 0. So we would get one solution, namely this one in that case. All right, now we haven't found a circle yet. I want to change the problem. I want to change this to minus 5 instead of plus 5, in which case I'm going to get minus 5 halves over here, and I'm going to get minus, instead of minus 40, I'm going to have plus 40, and so altogether I'm going to have 53/16. Right? X plus 3/4 squared, y plus a half squared is 53/16. Now, recall that equation for the circle was, we'll start with x minus x naught squared plus y minus y naught squared is equal to r squared. Well, we can put this in this form. If we write this as x minus a minus 3/4 squared plus y minus a minus 1/2 squared is 53/16. Well, that's going to be the square root of 53/16 squared. So this is a circle centered at the point minus 3/4 minus 1/2 with radius equal to the square root of 53/16. And it's clear here that what we've just done is completely general. That's to say, if we start with ax squared plus bx plus by squared plus cx plus dy plus e, and where a and b are equal, so the x squared term and the y squared term are equal, then we can divide by a, end up with something that looks like this, complete the square. If we end up with a negative number when we're done with this, it's going to have no graph whatsoever. There are going to be no points x and y that satisfy it. If we end up with 0, we're going to have 1 point that satisfies it. And if we end up with a positive number, then we're going to have the equation of a circle centered at the point given like so, with a radius r equal to the square root of that number. I want to talk at this point a little bit about graphing equations. The graph of an equation, first of all, an equation is some expression in x and y equal to some other expression in x and y. That's an equation in x and y. So you've got some sort of expression of x and y is equal to some other expression in x and y. And clearly, you could bring everything from this over to this side, and so that we could have an equation in x and y. Some expression in x and y is equal to 0. The graph of an equation is the set of all pairs x, y, such that the equation holds. Generally, if you've got some sort of an algebra equation involving x and y, the graph, or involving trig functions or general arithmetical relationships, the graph of an equation is going to look like some sort of a curve or curves. Right? We're not going to spend a lot of time at this point graphing equations, but there are several things that you can do if you've got an equation and you need to graph it. One of them is to rule out certain areas where the graph doesn't occur. For example, this graph is never up here, or over to the right over here, or down here, and over here. It's located inside of here. It may be that the equation is more complicated and we can't rule out this area. It may be that it goes on in this direction here, like so. Right? In which case we can still rule out some areas where you don't need to look for any points that satisfy x, y, that satisfy the equation. A second thing that you can do, of course, is the obvious thing, and that is to put a value of y in here and find out if there are any values of x that satisfy it. And similarly, put a value of x in. That's to say, plot some points. Now, the problem with this, of course, is that it's hard to tell when you've plotted enough points to be able to tell what the equation is. So graphing equations is not a simple matter. Right? There's a second thing that you can do here, and this will hold in general for the equations which we will be looking at, namely equations which describe functions. You can look for certain symmetrical aspects of the equation. In particular, for example, it may be that whenever a point x, y is on the graph, that you also have the corresponding points down here, x minus y. Right? In that case, the equation is said to be symmetric the x-axis. Right? If xy on the graph implies that the point x minus y is. And that's a great aid in graphing the equation, because then you only need to graph the upper half, and the lower half can be gotten by the symmetry. A second symmetry that sometimes can be recognized is the symmetry about the y-axis. If whenever xy is on the graph, then what? Minus xy is on the graph. Then you'll have symmetry about the y-axis. That's to say, the equation is said to be symmetric about the y-axis if xy on the graph implies x minus y. I'm sorry, minus xy is on the graph. Right. An example of this would be something like x equals y squared. Whenever you have a point xy that satisfies this, then, oops, y equals x squared, huh? An example of this would be x equals y squared. Whenever you have got a point xy on the graph, then xy minus y is also on the graph. Here, whenever you have got a point xy on the graph, then minus xy is on the graph. And so this is symmetric about the y-axis. A third type of symmetry consists of symmetry about the origin. That's to say, whenever xy is on the graph, also you have got the corresponding points down here. The point minus x minus y. If it's on the graph, then you're said to have symmetry about the origin. Or the equation is said to be symmetric about the origin if whenever xy is on the graph, then also minus x minus y is. An example of such an equation would be x squared equals y squared. Or xy equals 1. Right. There's something that's worth noting about these symmetries, and that is that you can't have either two of them without also having the third. If you've got symmetry about the x-axis and about the y-axis, then you also have symmetry about the origin. That's because whenever xy is on the graph, then x minus y is, and so consequently, since x minus y is, minus x minus y is on the graph. So when you have these two, you also have symmetry about the origin. When you have symmetry about the x-axis and symmetry about the origin, right, then this point is on the graph and this one is, and you also have symmetry about the y-axis. Or when you have symmetry about the y-axis and about the origin, you clearly also must have symmetry about the x-axis. So whenever you find two of these, the third one is already there. We want to look at a particular type of equation called a quadratic equation, and this should be familiar to most people from algebra. It's an equation of the form y equals ax squared plus bx plus c. And the graph of such an equation is called a parabola. It's a U-shaped curve, And if a is greater than 0, the parabola is going to open upward. If a is less than 0, the parabola may open downward. So either of those two cases here, when a is less than 0, here when a is greater than 0. If a is equal to 0, this equation becomes that of a line. If you interchange the x and the y in this equation, then you have parabolas that open either to the right or to the left. We'll just consider this case right here for the moment. Okay. A very important thing with respect to this, besides being able to graph them, which is not going to turn out to be too difficult, is to be able to find out when this crosses the x-axis. That is to say, when is ax squared plus bx plus c equal to 0. I'm going to derive this important formula right now, but it is one that you should have memorized and be able to say as quickly as imaginable. To solve this, I want to first of all subtract c from both sides and divide everything by a, so that I'm going to get minus c is equal to, I have bx, and I have ax squared, and I want to now divide by a, so I have b over ax minus c over a. Now what I wish to do is to complete the square of the left-hand side and make this a perfect square. And recall the way to do that is to take this quantity, divide it by 2, and square it, and add it on, so that I have x squared plus b over ax plus b squared over 4a squared. Divide this by 2, I have b over 2a squaring, I have b squared over 4a squared is equal to minus c over a, and now it's not fair to just add this to this side without adding it to the other side. So plus b squared over 4a squared. Now this is a perfect square. It's the square of x plus b over 2a. So this squared is going to be equal to, now I'm going to put everything over 4a squared here. So that I'm going to get b squared on the one hand, and I'm going to get minus 4a times c. I have to multiply numerator and denominator here by 4a. Now what I want to do is take the square root of both sides of this so that I get x plus b over 2a is equal to, in the denominator here, 4a squared is perfect squared. I'm going to write it as 2a. And now I must consider all possibilities here, so I need to consider that either plus or minus the square root satisfy this. Let's say x plus b over 2a is going to be equal to plus or minus the square root of b squared minus 4ac over 2a. And finally then x is equal to, bringing the b over 2a to this side, subtracting it, we get minus b over 2a, we'll put this over the common denominator, plus or minus the square root of b squared minus 4ac. This is a formula that's important to algebra, as your social security number is to you. It should be memorized so that you can say it really quickly. X is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. It's also worthwhile being able to use this in a variety of contexts when you wish to solve an equation of this form. There are a couple things to note about it. If this quantity inside the square root is negative, then there are no solutions. That would represent the fact that this came from an equation like this, where it did not cross the x-axis. There were no solutions. If the quantity inside the square root here is 0, then there is exactly one solution. That would represent the fact that this came from an equation where the parabola just exactly touched once the x-axis. But if the quantity is positive and there are two solutions, that represents the situation where the parabola crosses the x-axis twice. Secondly, If there are two solutions, you can note that one of them is at minus b over 2a plus this quantity, and the other one is at minus b over 2a minus this quantity. So that the two solutions are symmetric about the quantity minus b over 2a. Minus b over 2a is always going to give you the x-coordinates of the lowest point in the parabola when the parabola opens upward, or the highest point if it opens downward. This point is called the vertex. And if you plot it first, the resulting parabola is symmetric about that point, and it's easy to plot a few additional points, perhaps these, if there are such points, to the right and to the left to get a picture of what the parabola looks like. Now, I mentioned that you should be able to use this equation whenever you see it, so that, for example, if the letters are changed, you have something like s squared plus 4s minus 6 equals 0, you should be able to put that into this formula and say that this is going to occur when s is equal to minus b, that's minus 4, plus or minus the square root of b squared is 16, minus 4ac, 4 times minus 6 times 1 is going to be plus 24. Well, it's going to be minus 24, so we have minus 4ac over 2 times a. So that the solutions to this are minus 2 plus or minus the square root of 40 over 2. Right? Getting that immediately from this equation right here. Again, this should be memorized. One of the things that we're going to be dealing with throughout calculus are functions. Functions have been around for quite a while. The idea of a function has, and you will find, if you look around, old definitions of functions and new definitions of a function. I prefer the new, but I will give you an old definition of a function. A function is a correspondence which associates with each element in a domain set one and only one element in a range set. That's a function, according to the old definition. And there are some problems with it, but there are major problems with it. There's nothing particularly meant by domain set and range set. The idea basically is that there's one set and another set, and the function corresponds with the elements in this set, a given element in the second set. There isn't the first set's called the domain set, and the second the range set. The question which arises, of course, is what does correspondence mean and what does associates mean? Now, some people like to use the word rule up here for correspondence, but that assumes to a certain extent that you have got to have an explicit rule in order to have a function, and that generally isn't considered to be the case. Anyway, what does correspondence mean and what does associates mean? And if you think about it, correspondence doesn't mean anything. You could just as easily read this as a function is something which associates with each element in a domain set. And then the final question then is, what does the word associates mean? And the word associates means pairs. With each element in a domain set, it pairs up with that element, one and only one element in a range set. So better here would be something and pairs. Right? Although the more modern approach is to consider the function to be a collection of pairs. so that a function is a set of ordered pairs xy, if you want, no two of which have the same first element. That's to say, no two distinct pairs in the set have the same first element. For each first element here, there's only one second element possible. The first elements are called the domain. The second elements the image. The set of all second elements are called the image of the function. The range is any set that contains the image. It's usually a natural set where you would look for the second elements to occur, but it might not consist of all of those elements. All right. So a function is a set of ordered pairs, no two of which have the same first element. We'll write functions usually with f, g, or h, or if we need a lot of them, f1, f2, f3, so forth. Right? And if there is a rule that tells you what the second element is given the first element, then we will write y equals f of x. Right? Where f of x is supposed to be something that tells you a unique y for a given x. And consequently, we could also write that f, the function, is the set of pairs xy such that y is f of x. The graph of a function is special in the following sense, that if a point xy is on the graph, then there can be no other point on the graph of that function on this vertical line that goes through xy. So one way to describe a function when we're dealing with pairs of real numbers is that a function is a collection of pairs of real numbers so that the points in the plane corresponding to those numbers satisfy that each vertical line intersects the sets in at most one point. There's no second point down here. There may be, of course, a second point over here. Examples of some functions. Some of the things we've already looked at are functions. The equation of a line which is not vertical is a function. So that, for example, y equals mx plus b, or in particular, y equals 3x plus 4 is the graph, has a graph which is a function. This describes a function. Right? Likewise, a parabola opening upward. Y equals ax squared plus bx plus c is a function. Or in particular, let's say y equals 2x squared minus x plus 7. Here, it's very clear algebraically that given a number x, if you square it, you get a unique number. You multiply that by 2, you get a unique number. You subtract the original number, you get a unique number. You add 7, you get a unique number. So that this corresponds to each number x, one and only one number y. Here, in both of these cases, the domain set is considered to be the natural domain set unless it's specified otherwise. That's to say, this is defined for all numbers x as is this. For all numbers x, there's a point xy, so that the domain is a collection of all numbers. Sometimes it's necessary to figure out what the domain of a particular function is. Y equals the square root of x plus 7, for example, is an example of a function. You take a number, you add 7, you take the square root, you have a unique answer. The natural domain for this function is the collection of all x for which this quantity can be defined. That's to say, in order for this to be defined, x plus 7 must be greater than 0, or x must be larger than minus 7. So minus 7 to, or equals to, so minus 7 to infinity is the natural domain. The natural domain is all of the elements x for which the function makes sense. Now, sometimes you don't want just the natural domain. You might want to, for example, consider this function here, but not for all values x. Y equals 3x plus 4 with x, let's say, greater than 0. This collection of pairs is a different collection than this one. And so consequently, those are two distinct functions. Two functions are different if they involve two different sets of pairs. That's going to become an important distinction. It doesn't look like as if it's important at first, but it turns out that it is. So here's an old definition of a function and a new one. All right, we want to look at some specific examples of functions. We already know that it's a linear function. F of x equals mx plus b is a function. Or in particular, f of x equals 3x plus 4, for example. Likewise, a quadratic defines a function. G of x equal to ax squared plus bx plus c. Or in particular, for example, g of x equal to 2x squared minus x plus 10. In general, what's happening here is that when you take a number x and you square it, you get a unique number. So if we square the number and multiply a number by a number, we again get a unique number. Addition and subtraction give you unique numbers, and so the combinations like this are going to give you unique numbers. In particular, we could have this a cubed term and a fourth term and a fifth term, or however high a power of x we wanted to here. It would always result in a unique number, and we would have a function. A function, for example, let's say of the form a0, a constant, plus a multiple of x, plus a second one of x squared, plus and so forth, and finally one of x to the nth power. Such functions are called polynomials. And the resulting function is defined and has a natural domain which consists of all real numbers x. We could also define a function by taking one polynomial and dividing it by another polynomial. So that in general, if the first polynomial looked like a0 plus a1x plus an x to the n, the second one looked like b0 plus b1x plus and so forth plus b sub m x to the mth power, then the result would be a function which would be defined and have a natural domain at all numbers x, except for those where the denominator was equal to 0. Such a function is called a rational function, because it's the ratio of two polynomials. The square root of a number x is a function. Given a number x, by the square root we mean the positive square root, and so that this is a function. Right? It's a unique square root. For even roots, for that matter, we will always mean the positive roots, so that the even root of a function, of the number x, is a function, or in general, the root, h of x equals to the nth root of x is the function. When the root is even, the domain of the function is going to be the numbers from 0 to infinity. When it's odd, it's going to be defined for all real numbers. It's possible to take an odd root of any real number. Okay, we want to look at some possible combinations of functions, and these are given as follows. The first are very natural. If we've got two functions, f and g, we can then look at the function which is f plus g of x. And this is going to be defined at a point x by f of x plus g of x. Since f gives a unique value when you apply f to x, and g does also, in addition gives you a unique number, then f plus g is a function. And the domain, which I write with a script letter D here, of f plus g is going to be equal to the domain of f intersected with the domain of g. That's to say, in order for f plus g, this is the natural domain, in order for f plus g to be defined, f must be and g must be. Actually, even if it's not the natural domain, if f is defined and g is defined, then the function f plus g it means that it's defined on the set of x where f is defined and g is also. All right? We can do the same thing for minus. And the domain of f minus g is going to be the domain of f intersected with the domain of g. A constant times a function. By the function cf, we're going to mean the constant c multiplied by f of x. And the domain of cf is exactly the same set of x as the domain of f. The product of two functions. Multiplication is unique. So we've got two functions f and g. We can define f times g by f of x times g of x. And again here, as with addition, the domain of f times g is going to be the domain of f intersected with the domain of g. F must be defined and g must be defined, and then f times g will be. F divided by g will be the function at x, which naturally enough is f of x divided by g of x. And its domain is going to be the domain of f intersected with the domain of g, along with, we can't have g of x equal to 0 here. Set of x such that g of x is not equal to 0. That's the domain of f divided by g. So there's a final division gives you a unique number, so this is a function. There's a final combination of functions that results in functions. This is called composition. F, little circle is written here, composed with g at x is equal to f of g of x. Given a number x, g of x gives you a unique number. If f is defined there, then f gives you a unique number. So this gives you a unique number, f of g of x, for each number x. The domain of f composed with g is the domain of g. First of all, g must be defined. And then also, an element g of x must be in the domain of f. So that's along with the set of x such that g of x is in the domain of f. Right? So that's the domain of f composed with g. These are going to occur quite frequently, and you're going to need to be able to recognize them. As an example, if f of x is the square root of x, and g of x is 2x plus 7 then f composed with g is going to be the square root of 2x plus 7. G composed with f is not always the same as f composed with g. In this case, g composed with f at x is going to be equals to 2 square root x plus 7. But they're not the same function. It's easy to check that they're not by putting a particular number in here for x to see that you do not have the same collection of pairs. Here are some combinations of functions that result in other functions. Before we proceed further into the subject matter of calculus, before we even start, I want to say something about factoring polynomials. In particular, the following result is very useful. That is, that if p of x is a polynomial, so p of x, a polynomial, is given, then p of a number a, is equal to 0 if and only if x minus a is a factor of p. That is, if and only if p of x is equal to x minus a times q of x. Well, q of x is another polynomial. I want to show that this is the case. This frequently can be used to determine that, okay, you can divide x minus a out of a polynomial because you know that the value of the polynomial at a is 0. So the first situation here is real simple. Suppose p of x equals x minus a times q of x. Well then, if I put a in here, p of a is equal to a minus a times q of a minus a is 0, so it's equal to 0. So if p of x can be factored like this into x minus a times q of x, then p of a must be 0. All right, the harder part here. Suppose p of a is equal to 0. Right. Then what we want to do is to divide x minus a into p of x. And I'll show you by an example. If we do that, we can then write p of x as x minus a times q of x plus a remainder. Let's take a look at an example. Let's suppose we wanted to divide, let's say, x minus 3 into 2x cubed plus 7x minus 1. You do this in a sort of a natural fashion. There are more sophisticated ways of doing it, but you can just do it in a straightforward fashion. X into 2x cubed is going to be 2x squared. We multiply here and we get 2x cubed minus 3 times 2, 6x squared. Subtracting here, there's no x squared term in this one here, so it's 0x squared minus 6x squared is 6x squared. And if we divide x minus 3 into 6x squared plus 7x minus 1, we're going to get, what, plus 6x. Multiplied here, we get 6x squared minus 18x. And subtracting here then, we get 7x minus a minus 18x is 25x minus 1. And x minus 3 into 25x is going to be 25. Multiplying, we get 25x minus 75. Subtracting here. Minus 1 minus 75 is going to be 74. So that says that 2x cubed plus 7x minus 1 is the product of these two polynomials plus an additional 74. 74 is the remainder. It's clear from that example that you could take any polynomial of the form ax plus b degree 1, divide it into a polynomial of a higher power, and get one of a lower power plus a remainder which is a constant. So, if we suppose that we have done that, p of x is equal to x minus a times q of x plus r. But now we know p of a is equal to 0. P of a, which is 0, is equal to a minus a times q of a. Just putting a in here wherever I find the x, plus r. Well, a minus a is 0, so that this says that this is equal to r. Or r is 0. Well, if r is equal to 0, then p of x is equal to x minus a times q of x plus 0, and we've established the other direction holds. So again, if you've got a polynomial and you establish the fact that the value of the polynomial at a particular point is 0, then x minus that point, x minus a, is going to be a factor of the polynomial. And you can factor it in this fashion like so. Having polynomials in factored form is frequently useful. Okay, we want to take a look at some examples of functions which can be readily graphed. And the first of these, of course, is really simple. These are the type of function you should be familiar with to some extent. F of x equals x squared. The graph looks like this. This is 1 and minus 1, like so. The graph goes through these 2 points here and through 0. It's a parabola, of course, opening upward, like so. Symmetric about the y-axis. Other functions that you should be able to graph are other powers of x. In particular, the even powers look somewhat like f of x equals x squared. F of x equals x to the 4th is also 1 at 1 and at minus 1 and 0 at 0, except that when you take the 4th power of a number, it gets large faster than the 2nd power when the number is larger than 1, and it's smaller than the 2nd power when the number is between minus 1 and 1. And the graph looks like this. Again, this is a function which is symmetric about the y-axis. The similar situation here, of course, holds for f of x equals x to the 6th, or f of x is any power, any even power of x. F of x is x to the 6th, gets larger still when x is larger than 1 and smaller between 0 and 1, and it's symmetric about the y-axis. So. Okay, the odd powers. F of x equals x cubed is 0 at 0. At 1, it's 1. At minus 1, it's minus 1. And the graph looks like this. At 2, it's 8. And it increases like so. For the negative numbers, it's going to be negative. And it's symmetric about the origin. So that once you've drawn the right-hand side of f of x equals x cubed, the left-hand side is just symmetry through the origin. For the 5th power, if we take the 5th power of x, it's also 1 at 1, and at minus 1 it's 1. And the 5th power increases more rapidly than the 3rd when x is larger than 1, and it's smaller when x is between 0 and 1, and now it again is also symmetric here and looks like this. f of x equals x to the 7th. Right? Similar picture. And all the odd powers of x, right? They're closer to the x-axis between 0 and 1, and then they're larger when x is larger than 1 than the previous odd power. So the third power, fifth power, and seventh power. Right. The roots. F of x is x to the 1/2, or square root of x. Right. Well, the square root of x is only defined for positive x, and it is defined to be the positive square root. And this graph looks like this. At 0, it's 0. At 1, it's 1. Right. And as x increases, the square root of x increases. The graph looks like so. Right. And this is really half of a parabola because what? If y equals square root of x, then x equals y squared. And so this is the parabola x equals y squared in this direction right here. Right. For the fourth root of x, x to the 1/4, the fourth root of a number is smaller for numbers larger than 1. It's 1 at 1, and it's larger for numbers between 0 and 1. And then similarly here for the sixth root of x, x to the 1/6, the graph looks like this. For the even roots of x, the graph only has points in the first quadrant and looks like these. For the odd roots, the situation is different. F of x equals x to the 1/3, or the cube root of x. Right? You can take the cube root of 1, and it's 1, and 0 is 0. The cube root of minus 1, though, is also defined. It's minus 1. And the function looks just like the function y equals x cubed if you were to take it and flip it, interchanging the y-axis and the x-axis. So it looks like so. The fifth root, or the fifth root, gets smaller for x's which are larger than 1. It's smaller than the cube root. But for x's which are less than 1, it's greater than 0, it's larger. The fifth root has the same type of shape. Looks like so. The seventh root, same story. And similarly for all the odd roots. The seventh root is smaller than the fifth root, the odd one, and it's larger when x is between 0 and 1. This again is symmetric about the origin. Each of these odd roots are symmetric about the origin. So these are a few functions involving x to the nth power whose graph you should know. Okay. We want to look at some other exponential or powers of x, and the graph of x to the minus 1. F of x equals x to the minus 1 looks like this. It's not defined at 0. This is 1 over x. At 1, it's 1. And as x gets larger than 1, it gets very small, but still positive. And when x gets very small, it gets very large. And the graph looks like that. For the negative numbers, at minus 1, the value is minus 1. And this function is also symmetric about the origin. And the graph looks like so. X to the minus 2. This is to say 1 over x squared. This function is always positive because the denominator is always going to be squared. And it's not defined as 0. And at 1, it's 1. And at minus 1, it's 1. And the function is symmetric about the y-axis. And as x gets large from 1 on, the function gets small. And as x gets close to 0, the function gets larger. And since it's symmetric about the y-axis, we can just draw this in like so. That's the function. F of x is equals to x to the minus 2, or 1 over x squared. X to the minus 4 or 1 over x to the 4th has a similar graph. It's going to be 1 at 1 and at minus 1. It's also going to be symmetric about the y-axis. When x gets large, this quantity is smaller than 1 over x squared and looks like this. And when x is small and closer to 0, the quantity is larger than 1 over x squared and looks like that. And then by the symmetry here, like so. And so you have a similar picture here then for x to the minus 6th, for example. It's smaller than x to the minus 4th and larger over here, likewise here. For f of x equal to x to the minus 3, or 1 over x cubed, the picture is very similar to 1 over x. The function is 1 at 1 and at minus 1, and it's symmetric about the origin. And when x is larger than 1, this function is going to be smaller than 1 over x, and so it's going to look like so. And when x is between 0 and 1, it's going to be larger than 1 over x, and will look like so. And similarly over here, it will be up there, and then underneath the graph of 1 over x. It's a good idea to know what the other exponential functions look like, where you're taking x to a power. X to the minus 1/2, or 1 over the square root of x. If f of x is equals to x to the minus 1/2, the square root of x is only defined for x greater than 0, and then it's going to be positive. And so the domain of this function is going to be from 0 to infinity. And when x is 1, the square root of x is 1, and so that this quotient is 1. And as x gets larger, this gets smaller. And so 1 over the square root of x looks like this. Between 0 and 1, as x gets to be small, the square root of x is small also, and the graph looks something like this. It's not defined any place except for here. X to the minus 1/4, right? Or the 1 over the 4th root of x. Well, the 4th root of x is smaller than the square root, and so 1 over the 4th root is going to be larger for numbers larger than 1. It's going to look like this. It has approximately the same shape as 1 over square root of x when you're drawing it. It's larger over here and smaller here. And the same thing is true then for the other even roots, the reciprocal of the other even roots of x. X to the minus 1/3, or 1 over the cube root of x. Here we can use the fact that the cube root of x looks something like this, drawing it in lightly here. And now if we take the reciprocal, it's going to be defined at every real number. And it's going to be 1 here and 1 here at 1. And as x gets larger, it's going to get smaller. The graph is going to look something like this. And this is also symmetric about the, the cube root of x. That's x cubed. The cube root of x looks like this. 1 over the cube root of x. The cube root of x looks like this. 1 over the cube root of x is going to be again 1 at 1 and minus 1. And then as x gets larger, 1 over the cube root of x is going to get smaller. And as x goes to 0 here, it's going to get larger. So that 1 over the cube root of x looks like this. And down here like so. Okay. And 1 over the fifth root of x is going to have a similar shape, except that the fifth root of a number is going to be smaller when the number is larger than 1. And it's going to be larger when the number is between 0 and 1. And this again is going to then be symmetric about the origin. So 1 over the cube root of x, 1 over the fifth root of x. And the other odd roots of x, the reciprocals of them, are going to have similar graphs like this. Okay. These are functions, these powers of x are functions which are readily graphed by just analyzing what happens where the function is getting larger and where it's getting smaller and where it's not defined. Take a look at some other examples of graphs where you can get some ideas to what the graph looks like. Let's take a look at the graph of f of x is 1 plus, let's make it x plus 1 over x. Right. Now, here this function is the sum of two other functions, and you can graph the function y equals x. You can also graph the function y equals 1 over x. This is at 1, looks like this. And since it's the sum of these two, you can sort of geometrically add them and see that what happens here is that you get the function as it's 2. And that as x gets large, this part gets small here, and we add this to the number x. And so the function goes up like this, like so. And as x gets small, you're adding smaller and smaller quantities to this, 1 over x, and the graph looks like this. And then similarly on the negative side, you can either add these graphically, getting minus 2 here, or note the fact that this function is symmetric about the origin, and so that its graph must look like so. So the graph of f of x equal to x plus 1 over x consists of these two curves, this one and this one. How about f of x is x cubed minus x? Well, again, you can graph x cubed. Looks like this. And here's x. Should look a little more like this. In fact, if that's x, then this must be the point 1, 1. Both of them go through the point 1, 1, and both of them go through the point minus 1, minus 1. So when we take a look at x cubed minus x, we can think of subtracting these. So that, for example, x cubed minus x is going to have to be 0 here, and it's going to have to be 0 here, and it's going to have to be 0 here. Right? And now when we take x cubed minus x, here x cubed is less than x. So x cubed minus x is going to be negative. Right? X cubed is larger than x over here, so it's going to have to be positive. X cubed is larger than x over here. So this is going to get to be positive, and it's going to look more or less like so, and over here, like this. All right. This function also is symmetric about the origin, and so that once we've drawn the graph on this side, we can just copy There's a flip over of it on the other side. How about